Hey guys, Mr. Roden here. Hope everyone had an awesome Thanksgiving break. It's been a while, and hope everyone is doing well at home. I know we're doing some asynchronous, or not asynchronous, but today we're asynchronous, but we're doing some remote learning now that we're kind of back at home now. But hopefully we can make this great experience. I'm looking forward to it. I'm going to be working most of the time from home here. You can look around me. Not much going on in here. It's a very secluded area, so hopefully it'll be a good place where I can help you guys out with your math and teach you from my home to your home. So sound good? All right, so let's go ahead and take a look at our agenda for today. All right, so our learning target is I can use the perpendicular bisector theorem and its converse to solve problems. So our agenda today is good thing, and then we're going to do a warm-up. Then we're going to look at the homework bucket. And then after that, we'll do lesson 4.4. I think I want to look at the homework bucket first and then do the warm-up. I think I want to start changing that up. I think it's better to look at the homework bucket first and then get into the warm-up. Okay, so let's go ahead. Good thing. So what's my good thing? My good thing is I had a wonderful Thanksgiving. It was small. A lot of Thanksgiving celebrations right now are very small. We just had my two daughters and my wife and my mother-in-law, and we just had a great time. It was very mellow. The food was fantastic, and we just kind of hung out at our house, and we put up our Christmas decorations. So our house looks very Christmassy. My wife said it looks like Christmas threw up in our house. It's just so Christmassy right now, and it's really cool. Oh, and then we watched our favorite Christmas movie. And what is the greatest Christmas movie of all time? The Elf. Everyone knows that. Okay, if you don't agree with me, then you're just wrong because it's a postulate. It's just an assumed fact that The Elf is the funniest Christmas movie around. Okay, all right, excellent. So that's my good thing. Just had a great break, and now I'm ready to get back to teaching again because that's what I do. I'm a math teacher. All right, let's take a look at the homework bucket real quick, shall we? Let me go over here. Let me look at the homework bucket here. All right, the homework bucket. Let's go up to your second quarter homework bucket. All right, so the homework bucket is angles and transversals homework in Delta Math. Now, that was right before break. And you know what I'm going to do? I'm going to pause this video really quick, and then I'm going to add one to it. So let me pause this really quick. Oh, sorry about that, guys. So let me go back to the homework bucket here. Okay, so in your homework bucket, let's see what we have. Well, there's 3 assignments that look like they're open. This 4.1, 4.2, I'll take a look at this today because it's we'll say it's Monday. Make sure that's in. I believe that's probably already expired. Angles and transversal Delta Math, that's already expired. I did have some of you guys email me and say you struggled with it, so I'll take a look at that. And so I'll look at your grade on that. And then, let me go back. If you struggled with the angles and transversals homework, here's what I'm going to do. I'm going to put that grade in. If you come see me during, I'm going to put it into Q just like what I see in Delta Math. And if you want to raise that grade, come see me during JAG time, or you can email me during the day, maybe during lunch or something, and we can get on WebEx and we can go over it. And then I'll give you those points back. But I don't want to just give you the points. I know some of you said that you've been working for an hour and things like that. And I agree with that. And I'll give you that. I'll give you some of the credit. But in order to, what I'll probably do is if you emailed me and said you worked an hour, I'll give you 75%. And then if you want to get the rest of the grade, you need to come see me because obviously there's something I need to help you with. And so we can come in on WebEx. So if you don't like your grade and you emailed me and you said you got, you put an hour on it and you're still struggling, I'll bump that up to 75%. But if you want to get the 100%, then you need to come see me, schedule a time with me, just email me and let me know, and we can set up a time and we'll get on WebEx and we'll look at some problems and help you out there. Okay. So, cause I want to work with you personally on that to make sure we understand that stuff before you get to a test and it really catches up with you. And then today's homework is going to be basically just describing your learning. It's going to be one essay question. And I will say this, it's got to be 5 sentences. at least 5 sentences. If you short me, if you do like 1 or 2 sentences, I'm not going to give you full credit. In fact, I'll probably give you very little credit. I need at least 5 sentences. So make sure you're being pretty specific about what you learned today. So pay attention to today's lesson, and that can help you get this question down. So that's your homework for today, and that homework is due Thursday, this Thursday, December 3rd at 11:59. So make sure you get that done. All right, cool. It's just one question. It's an essay question about what you learned. All right, so let's go on to our warm up. Now we've already done this before, but I want to go back to creating a perpendicular bisector. Okay, because that's what we're going to talk about today. We're going to talk about perpendicular lines and perpendicular bisectors specifically. So here, there's 2 ways you can usually get a perpendicular bisector. You can be given, and a lot of times what's going to happen in a problem is they're going to say line blank is a perpendicular bisector of segment blank. Or you can always construct one. So a construction is a logical reason in geometry. So I just want to kind of review this. It's very simple. I think it was Noah, and I may have been, I can't remember who else, Alden maybe? Noah, and I can't remember, someone else went and got some points for this. So it's a very easy construction. So the first thing you want to do is you want to go ahead and construct a segment. Okay, so here's my segment. And I'm not going to make it too long, because if I make it too long, I might not be able to fit it in this picture here. All right, so we'll call this segment AB. Okay, keep it pretty simple. I'll move this over here. I'll even put some points on it. Clear that out. Put some points on this. Point here, even though we don't really need those dots. Sometimes it's nice to have it. Okay, so we'll call that segment AB. Get rid of my compass for a second. So this is A. I think the key is not lifting up your pen when you're drawing it. All right, AB. Okay, and then what we're going to do is, so we want to construct a perpendicular bisector of this segment. Now remember, it can't be a line. There's no way to bisect a line because lines go on forever. So this has to be a segment that you're going to bisect. The thing you make, though, can be a line. The line can be a bisector, but it has to bisect a segment. Hopefully that makes sense. So a segment can be a bisector, or a line can be a bisector, but you have to bisect an actual segment. So all we do is we just pull it up. I think I'm going to change my color here to red. And we just take our compass and we open it up over halfway. And you just kind of eyeball it. Okay? And so now I'm going to go ahead and eyeball that, and then I'm going to lock my compass. I'm going to keep that lock, and then I'm just going to go ahead and make an arc. This is why hopefully I'll be able to fit it in here. And then what I want to do is I want to take that same setting, and I want to put it on A, and then I want to make an arc. And I'm barely getting it there, but I think it still works. And then so what we got when we did that is, let me get rid of my compass, change the color, get rid of the compass again. And so remember what we did when we got that, so we'll just call this intersection of arcs is C, and way down here, this is D. Okay, and all we do now is we just pull up a straight edge or whatever, and we just we construct a line or a segment, doesn't matter, through those 2 points, C and D. Now, what do we get here? So we get 2 very important pieces of information. If I know that line or segment CD is a perpendicular bisector of segment AB, then I get 2 very important pieces of information. All right. So the first piece of information is I get that this is a right angle. And now I get, that's what perpendicular means. Now, notice, guys, all of these angles are perpendicular. I'm going to put one right angle here, but all of these angles here at, let's say, I don't know, let me just call it E. We'll just call this point E, where the intersection is. All the angles at point E are right. And you can see why. Well, we got a vertical angle, we got supplementary. It's pretty easy to see that we get 4 right angles here. So I'm just going to draw one, but just know all of these angles are right angles. Now, we also get another important piece of information. Let me change the color to, let's say, blue here. Get rid of that. I don't need that. I don't know why it always pulls the protractor up when I change the color. We get that AE is congruent to EB. Okay, or we can say the measure of AE is congruent. We could always say the measure, I don't even want to try it. Sorry, it's going to be messy. But the measure of AE is equal to the measure of EB. And that's just by definition. There's nothing we've done at all as far as figuring anything out. Just by definition, we get two very important pieces of information. We get a right angle at E, 4 right angles at E, and we get 2 congruent segment pieces after that. And that's just by definition of a perpendicular bisector. Sound good? Now, so what I want you guys to do is I'm just going to clear this out here. What I want you guys to do is I want you to go ahead and practice it. And what I want you to do when you practice it, because a lot of you have already done this, practice it doing one, don't do the line so that, see if you can do it on a slanted line like this, okay? So see if you can do it not on just like a horizontal line, but see if you can do it on a slanted line and see if you can still get it to work, okay? So that's your goal right now. So I want you to actually do this. I probably will just call on someone randomly. It won't be extra credit. It'll be a random. I'm just going to put your names in sticks or something. I'm going to pull out and just say, so-and-so, share your screen and do it. And so I want you to be able to construct a perpendicular bisector with a slanted line, a diagonal line, and not just a straight horizontal line. See if you can do it. All right, so right now I want you to pause the video and go ahead and practice perpendicular bisector on a slanted line. All right, cool. Well, welcome back. Let's go ahead and take a look at the lesson for today. Now, good thing done. Warm up done. Homework bucket done. Now let's look at lesson 4.4. Okay, so here's what I want you to do. I want you to go ahead and write this down. And so you're probably going to want to pause me here for a second. Let me read it out loud. And then I want you to write this down. And then I want you to draw this picture right here that I have drawn. So, and then we're going to talk about it. All right, so here's today. We're going to talk about the perpendicular bisector theorem. And let me read you the definition. If a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. Okay? So go ahead and pause me, write that down, and then draw the little picture because we're going to work with that picture a little bit. All right, go ahead. Hey, welcome back. Now, here's a couple things. Before we talk about it, the first thing there should be bells going off in your head is that we have a theorem here. A theorem always requires a proof. Now, I'm going to cheat a little bit on this proof. We're going to assume that there is a proof, and I'm not going to prove it yet. I will come back and prove it later. Now, the way the book, because I'm pulling these problems from your geometry book, the way the book is doing it is that they are using transformations, reflections, rotations, translations. They're using the rigid transformations to prove it. I like to use a classical geometry proof. The problem is we don't really have the tools yet in our geometry toolbox to prove it classically from a geometry standpoint. So here's what I'm going to ask you to do. Just know there is a proof. There is a proof. There's 2 different ways you can do it. You can do it through transformations, which we have in our toolbox, but I'm going to hold off until we can prove it using more of a classic geometry method, because transformations is kind of a modern way of proving geometric concepts. So I'm going to actually hold off on that. And then when we get to these really key ideas in geometry later on pretty soon, then I'll come back. So don't let me forget to prove the perpendicular bisector theorem when we get back to it. But so for now, we're just going to hold off on the proof, and we're just going to see why this is so important. So first of all, we got a perpendicular bisector here. Now, that's given. Who knows? Did they construct it? Is it just a plain old given? So before we kind of get into the theorem, I just want to by what are you given here? Okay, so notice when you're given a perpendicular, you're given that this red line right here is a perpendicular bisector. Okay, we get some very, very, very important pieces of information. The first thing, let me just kind of get rid of that. So if I know, so let's say I'm given that line DC is, or segment DC, what I'll call it a line, okay, because it looks like it has arrows on both sides, is a perpendicular bisector. I'm kind of abbreviating here. Perpendicular bisector of segment AB. We get two really important pieces of information here. Okay, the first piece of information is I get that all angles at C, are right angles. Right angles. So what I get here is I'm getting four right angles here. And like I said before, I'm just going to put one right angle symbol in here, but no, there's four of them there. Okay, so I'm getting four right angles. What else do I get? Well, I also get a very important piece of information that I know that AC is congruent to BC. Okay, I get that they're congruent. So why do I know that? That's just by the definition. This is just definition of a perpendicular bisector right here. So as soon as you're given that something is a perpendicular bisector, whether you constructed it or you're given it, you get two really important pieces of information just from the definition. Okay? And by the way, perpendicular is kind of a long, crazy word. And so what we're going to use is, let me draw this over here, up here. So let me just do it up here. We're going to use an upside down capital T to write the word perpendicular, to stand for the word perpendicular. So I'm probably never going to write the word perpendicular. I'm going to use an upside down capital T to symbolize it. So how could I do that? I could say, since this is a perpendicular bisector, I can say that line DC is perpendicular to segment AB. Okay, so I'm not going to use the word perpendicular very much. I'm going to use the upside down capital T, and that's pretty much a universal symbol for perpendicular. Okay, so cool. All right, so just a couple side notes here. Now, so this is what you're just given from the definition. Now, what do you get from the theorem? You get two or one, however you look at it. You get two or one very important pieces of information. You get that this distance, if D is on the perpendicular bisector, that you get that this distance from D to A is congruent or equal to the distance from D to B. Okay? You get that those two green lines I'm using there are congruent to each other. Okay, so you'll know that this is congruent to this, or they're going to have the same measure. So there's two kind of ways to look at it. You could say that segment AD is congruent to segment DB. Or if you want to talk measures, remember how we show measures? We just don't put the line over it. We can say the measure of AD is equal to the measure of DB. So you get that, and that would stand for anyone. So if D, but you could have multiple points on this. Let's use a yellow point here. Let's say we had the point E. Well, if we have the point E, then what I know is then I can say that this D to A is congruent to E to B. Now, I'm not saying the green lines are congruent to the yellow lines. I'm saying the two pieces of the green lines are congruent to each other, and the two pieces of the yellow lines are congruent to each other. Okay? So I'm not saying that DB is congruent to EB. That's not what I'm saying here. I'm saying the distance between E and A is always going to be equal to the distance between E and B if these points are on the perpendicular bisector. Now, one other point to make here, let's say we had a point that's off the perpendicular bisector. Let's say we had a purple point. Well, just by kind of common sense or whatever, the distance, let's call this point H, the distance between H and A is not going to be obviously equal to the distance between H and B because H is not on the perpendicular bisector where D and E are. Okay? So that's kind of what the perpendicular bisector gets. So when this is what you get from just the definition of a perpendicular bisector, and this is what you get from the theorem. So you get a little extra piece of information that those two distances are equal to each other if the point is on the perpendicular bisector. All right, again, the proof is coming down the line. Now, this is also a what we call a biconditional theorem because the converse is also true. So I'm going to go ahead and read it, and then I'll have you pause it, and you can write down just like you did with the perpendicular bisector theorem. So let me kind of, and then it's the same drawing, and we'll talk about what that looks like. Okay, converse of the perpendicular bisector theorem. If a point is equidistant from the endpoints of a segment, then it lies on the perpendicular bisector of the segment. Okay, so go ahead and pause Mr. Roden right now, and then go ahead and copy down this picture and theorem. Hey, welcome back. So let's take a look at this really quick. So first of all, what do we get? What do we get just from the straight up given here? So what we get from the given, let me do it in, I'm going to do, let's see here, I'm going to do blue. Change this color to blue right here. All right, so what do we get from the given? So the given is that the point is equidistant. So all we're given is that DA is congruent to DB. Okay, so we're seeing that DA is congruent to DB, and that's just given. So that's the given statement here. So we can now say if we draw a line between A and D, and we draw a line between D and B, what we get is from the given, from what we're told and given, that we know that these two distances right here are congruent. So this distance and this distance are congruent, and that's given. Now, if we know that these two are equal to each other, then we know that D must be on the perpendicular bisector of this segment AB. So this is what we're given. Now, what do we get? We get a lot. We get the reverse of last time. What do we get from that? From what do we get from the theorem? So we actually get everything we would have started out with the perpendicular bisector theorem. We get that DC is perpendicular to AB. In this case, I didn't make it a line, I made it a segment. Okay? Which means that C is a right angle. All angles at C are right angles. Okay, so we could put, if we wanted to, we could put a right angle symbol in here because we know that it's on the perpendicular bisector. But we also get that AC is congruent to BC. So now we get this. So we get some nice pieces of information here. Now, a side note, why is it so nice to get especially a right angle? Think about that for a second. When in math do we involve right angles? Especially if you notice we're getting triangles here. What do we not like about right triangles? We like about right triangles because right triangles can let us use the Pythagorean theorem. So if you've noticed here, we've made these right triangles, and we know they're right because they're perpendicular. And whenever you can apply the Pythagorean theorem, it is very, very, very useful. I cannot underemphasize how important this Pythagorean theorem is. In fact, it's so important that we're letting you use it right off the bat before we've even proven it in geometry. Okay, so just remember, a squared plus b squared equals c squared is absolutely ginormous in geometry. It's huge. It is the biggest thing ever. So we're actually letting you use it and apply it. Like the distance formula is just a squared plus b squared equals c squared on the coordinate plane. So we're letting you use it right away because it's so important, but we will prove it down the road. Okay, awesome. All right, so let's apply what we learned using the perpendicular bisector theorem and the converse of the perpendicular bisector theorem. Okay, so let's go ahead and take a look. So what I want you to do is go ahead, we'll call this example number 1. I just copied and pasted these, so I didn't put. Okay, so what I want you to do is go ahead and copy this down, and then we'll kind of apply this really quick and just kind of do a little bit of work. Okay. All right, so hopefully you have it copied down. And so let's just read the question and do the work. So it says AD is 10 inches long and BD is 6 inches long. Find the length of AC. Now, notice what you have right away. Okay, you know that, first of all, this distance from here, from A to D, is equal to the distance from D to C. Now, they even were nice and told you this is a right angle, but they didn't even need to tell you that, because if you know the distance from A to D is congruent to the distance or equal to the distance from D to C, you right away know that it's a perpendicular bisectors. So you know it's going to be a right angle. They didn't have to tell you that, but you also know that AB is congruent to BC. And the reason I put 2 slashes through and not 1 is because 1 was already used up with the given. Okay. All right. So now if we know that AD is 10 inches long, okay, then we also know that DC is 10 inches long. Now I may need that or I may not need that. Don't really know yet. BD is 6 inches long. So B to D is 6 inches long. And we want to find the measure of AC. So we want to find the measure of A to C. Now, remember, right triangles here this involves right triangles. Whenever we have right triangles, we can use the Pythagorean theorem. So we've got a nice right triangle here. We're going to find this side right here. So we need to find this side X, okay? And once we find X, we'll kind of talk about what we can do after that to find the length of AC. All right, so how do we do that? Well, we can just use this right triangle right here. So we can say X squared plus 6 squared equals 10 squared. So we get X squared plus 36 equals 100. And so simply solving for x squared, we get x squared equals 36. 100 minus 36, I believe, is 64. And then we can square root both sides. And so we get x equals 8. So now that we know that x equals 8, but since it's on the perpendicular bisector, we know AB is equal to 8, and we know that BC is equal to 8. So we can now say that the measure of AC equals 8 plus 8, which equals 16. And we're done. All right, so let's do the next one. Okay, so this one says, that B line B is parallel. Remember, this is our parallel symbol to D. So we know that B is parallel to D. And remember, when we put these arrows in here, that means parallel. And C is parallel to E. So let's do like that. And let's do like that. Okay. And the reason I put 2 and not 1 is because, remember, one arrow is parallel to the one arrow. 2 arrows is parallel to the 2 arrows. Okay. All right. So if we know that the measure of angle 1 is 50 degrees, so if this is 50 degrees here, and we know the measure of angle 5 is 90 degrees, so that's a right angle here. Use the diagram to find the measure of angle 4. So let me just highlight, we want to find angle 4. Okay, so, well, remember back what we've been doing. So if I look at angle 1, how are angle 1 and angle 2 related to each other? Well, if we use C and E, and since they're parallel, then we can say that angle 1 and angle 2 are congruent because of corresponding angles. They're in the same position. Top right here, top right here. So we can say that angle 2 is also equal to 50 degrees because C and E are parallel, and corresponding, when lines are parallel, corresponding angles are congruent. And then what we can do is we can say, well, 2 is congruent to 3, so 3 is 50 degrees because 2 and 3 are vertical angles. Now, we can see now that since 5 is 90 degrees, 3 plus 4, the measure of angle 3 plus the measure of angle 4 has to be 90 because it's perpendicular, like we said before. So this basically just boils down to taking 90 degrees minus 50, which means that we get, what do we get there? We get 90 minus 50 is 40 degrees, right? And we're done. So 9 minus 5 is 40 degrees, and we're done. So the measure of angle 4 equals 40 degrees. Cool. All right, so next problem, let's take a look at another one here. This one's not too bad. Okay, so use the diagram to find the lengths of BP. Find the lengths. BP is a perpendicular bisector of AC. So BP is a perpendicular bisector of AC. Well, that means that these two have to be congruent to each other. And then we know that QC is a perpendicular bisector of BD. So basically, and the book, I think, in my opinion, the book should not have said this. You should have known this by the transitive property. So if this is congruent to this and this is congruent to this, they're all basically congruent to each other. Okay? So suppose AP is 5. So we know that AP here is 5. What is the length of PC? Well, that's obvious. It's 5 because it's the perpendicular bisector theorem. So PC, the length of PC, so we can just say PC equals 5. Suppose AP is 5, we already told that, and BQ is 8, and BQ is 8, so we know that this is 8 right here from here to here. What is the measure of QD? Well, again, the perpendicular bisector theorem says that has to be 8 also. So pretty much a piece of cake. Okay? All right, let's take a look at this one right here. Use the diagram. We got PC. Okay, so PA is equal to PC. So PA is equal to PC. Use the diagram to find the lengths or angle measures of the described. The measure of angle 2 equals 38 degrees. So we know that this is 38 degrees right here, that angle. What's the measure of angle 1? Well, if we know that the distance between PC and PA is congruent, we know it's on a perpendicular bisector. Okay, that's the converse of the perpendicular bisectors theorem, which means we can say that this angle right here that's formed by angle 1 and 2 is 90 degrees. Since we know this, we know that it's a perpendicular bisector, so we can say that's 90 degrees right there. So we can just say 90 minus 38. We can do the math here. That becomes an 8. That becomes a 10. 10 minus 8 is 2. 8 minus 3 is 5. So we can say the measure of angle 1 equals 52 degrees. All right, let's take a look at the next one. Let's say PA, the measure of PA is 10. So from here to here is 10. And we know PB from PB is 6 right here. What is the measure of AC? Well, in order to do that, what we have to do is we have to look at this triangle first right here. This, let me highlight it. We have to look at this blue triangle right here, okay? And on that blue triangle, that's a right triangle. And remember what I've been talking about with the Pythagorean theorem. That's a really nice thing because we have a right angle because it's a perpendicular bisector. So we can say that a squared plus b squared equals c squared. Well, in this case, our a we can say that PB. So we know that PB is 6. So we'll make PB 6. So 6 squared. Plus, now we don't. Let's make this an x right here. X is the distance between A and B. Okay, so x is going to be the distance between A and B. So we'll say B will make x. So we'll say x squared equals, and then C is just going to be the hypotenuse, and that's going to be 10. That's going to be AP. So that's going to be 10 squared. All right. So now we have 6 squared is that's 36. Plus x squared equals 100 squared. And then we can just say, well, again, x squared equals, 100 minus 36 is 64. So we can say x equals 8. So if we know that this is 8, now what else do we know? We know since it's a perpendicular bisector, by definition, we know that BC also has to be 8. So we can just say that 8 plus 8 equals 16. Because remember, AC by segment addition postulate, AC is equal to AB plus BC. So this is 8 equals 16. Segment addition postulate. All right, find the measure of angle 3 and 4. Well, since it's a right angle, 3 and 4 has to be 90. So the measure of angle 3 plus the measure of angle 4, that's just equal to 90. That's just equal to 90 degrees, right? That's all that is right there. Piece of cake. You're just saying, hey, there's a lot of different ways to look at it. But remember, a perpendicular bisector, like I said before, you get 4 right angles there. Each corner at that point of intersection of the perpendicular bisector, each corner is going to be a right angle. Okay? All right, cool. All right, let's end this thing with a proof here. All right, so given that RS perpendicular, remember the capital upside down T is perpendicular. So given that RS is perpendicular to CD and AB is parallel to CD, prove that RS is perpendicular to AB. Cool, we can do that. That's pretty easy. Okay, so the first thing we're going to say is RS is perpendicular to CD, and that's a given. And so now we can say that the measure of angle RTD is equal to 90 degrees. And that's the definition of perpendicular. If it's 90 degrees, then it is, if it's a right angle, it's 90 degrees. So let me put some lines here. So this is line 1, that's line 2. All right, so now we can say that, let's get that other given in there in step 3. So now we can say that AB is parallel to CD. Okay? And why do we know that AB is parallel to CD? Well, we know that because it's given. Okay? And I'm going to make this a little longer here. I probably didn't know I was going to write so big here. And then number 4 is I can say angle RTD is congruent to angle TVB. Okay? And why do I know that? Because because they're corresponding angles. Corresponding angles. So remember, when lines are parallel, which they are, corresponding angles are congruent. All right. Let me move up here. Just a little bit here. All right. So step 5 is going to be that. Let's see. Step 5 is going to be that the measure. We can now say that the measure of angle R. Let me say, how about this? TVB equals 90 degrees. Okay? And so now, because that's basically substitution, right? Because if we know that RTD is congruent to TVB, then we can just substitute 90 in for each one of them. So sorry, guys, I'm running out of room and I want you to be able to see this. Okay, so my last thing, step 6, is now I can say that RS is perpendicular to AB. Okay? And why can I say that? Well, it's the definition of perpendicular. It's the definition of perpendicular. If an angle is 90 degrees or a right angle at an intersecting point, they are perpendicular. If you get a 90-degree angle right here, which we do, because basically what we did is we said, okay, since they're corresponding angles, I can move this one down, okay, and because they're congruent, but they're also right, so they're both right angles, therefore they're both equal to 90 degrees, so we can substitute a 90 in there, and so now we can just say that they're perpendicular because that is a right angle right there. Probably we can say they're perpendicular. We might want to actually take another step here. So I don't want to. So we can, now that we can say, we don't want to say, we can now say that angle R, hold on, angle TVB is a right angle. We probably want to say that before, and the reason we can say it's a right angle is the definition of a right angle. If they have a measure of 90 degrees, then it's a right angle. And then on step 7, we can say that RS is perpendicular to AB. And the reason we can say that is the definition of perpendicular. Because the true definition of perpendicular is that there's a right angle at their intersecting point. And so you don't want to go straight from 90 degrees to perpendicular. You want to go right angle to perpendicular. So you got to do that extra step in between. And by the way, on step y is equal to 90 degrees, that's substitution. Okay, let me go through this one more time to make sure we have it. RS is perpendicular to CD. That's given. Measure of RTD is 90 degrees. That's the definition of perpendicular. AB is parallel. That's given. Then we can say that angle RTD and TVB are congruent because of corresponding angles. And then we can say the measure of angle TVB is 90 because of substitution. If one of them, if RTD is 90, then TVB is 90. And then we can say that the angle of TVB is right because it's 90 degrees. And then we can say it is perpendicular because the definition of perpendicular is when two lines form a right angle at their intersecting point. And we're done. Okay, I think that's it for today. Hopefully this lesson doesn't go too long. I don't even know how long I've been going here with the pauses and everything I've had to do. But you guys have a great day. Remember to fill out that last question, and I'll do 5 sentences, guys. Hopefully, I think you've got enough information here to get 5 sentences out. So we'll see you later, and looking forward to seeing you guys from remote learning starting tomorrow. So we'll see you guys tomorrow, guys. See you later. Bye.